Work it, make it, do it, make sense.
Okay, so thank you, everyone. Thank you for inviting me to DevOps. It's the first time I've been to this conference. A good friend and colleague of mine, Steve Poole, who I think is in a parallel talk at the moment, has been trying to get me along to this for a couple of years now. And he asked me just a couple of weeks ago, actually, to come and talk at this event, and I said, sure, what do you want me to talk about? And he said, oh, just cool techie stuff and programming, and just be yourself. So with that fairly ambiguous description brief, I decided and had to think about it, and I thought I'd reflect on my own kind of journey in computing, how I came to work for IBM, and just a little bit of sort of a look forward as to where we might be going. Now, I'm a kind of nostalgic, retro kind of guy, so hopefully at least some of you might get the cultural references that I'm alluding to throughout the pitch. So I called this 8 bits to Qubits, why I love being a programmer and why I think now is the best time to be one. So I've been with IBM for a long time, as evident from my badge. And over the last quarter of a century, I've had the tremendous privilege and pleasure to work on some amazing technologies, some amazing teams, and see a lot of things happen in the computing industry over the last 25 years. Like, for example, I was the first person to create a website in IBM back in '93. I worked on some of our early computer vision and VR work with research, doing digital fingerprinting as well. I implemented MQTT, the first implementation, about 20 years before it became a standard. I worked on grid technologies and then web service technologies, probably the less said about that, the better, and then cloud technologies. And also had a great time working with the games industry, working with the teams that developed, in IBM, that developed the processors for the PlayStation 3, the GameCube, no, the Nintendo Wii at that point, and the Xbox. But in recent years, I've been focusing my attention on not so much the what, but the how, and working on DevOps transformation work, so I've been around the block a bit and got a few patents along the way, which is why I've got this title of Master Inventor within IBM. That's about helping people to come along as well. And I got elected into the IBM Academy of Technology about 10 years ago, which was an immense privilege. But why did I get into computers? And that's really what the premise of this talk is about. And to answer that, I have to take you back in time. So I'm a child of the 60s, but I grew up really in the 70s. So I'm going to take you back to the early 70s and Clacton Pier. Has anybody been to Clacton-on-Sea? And I'm not surprised nobody put their hands up. It was the nearest seaside resort to where I lived. And we spent inordinate amounts of time playing in the arcades there. And in the early 70s, arcade machines were pretty much the same thing that they had been for the previous 20, 30, 40 years. They were electromechanical. They were incredibly ingenious. Does anybody recognize any of these things? When I Googled for electromechanical games, I suddenly saw things that I forgot existed for about 40 years. But they were basically toys on rods and wheels and rubber bands, and you would control sort of tanks, real physical tanks, and it was incredibly exciting. But it was quite primitive. So I could attempt to make the same sort of thing using, airfix soldiers on lolly sticks and a 9-volt battery and a bulb for an explosion, with limited success. But it was at least a possibility. But then the late 70s started to change the feel of the arcades, and suddenly we saw the emergence of digital video games. And these were very exciting. The graphics were quite crude, but nevertheless it was stuff happening on a TV screen, which was completely different to what we'd been used to. And this trend of video games continued throughout the 70s and kind of was perfected when it got to games like this. This game is Monaco GP by Sega, released in 1979. And it was just incredible. I remember playing this and thinking, it can't get more real than this. This is the real thing. Incredible. But what's interesting about this is these video games were still ostensibly the evolution of the electromechanical games. They were purpose-built devices. They weren't really computers. They were very elaborate circuits built to do a specific task. And this is actually the circuit board schema for Monaco GP. They're incredibly rare. But what's interesting, if you have sharp eyes, we'll find that it's all just AND gates and OR gates and no CPU. Incredible what could be done, but as I said, not really a computer, a very hardwired device. And video games started to appear at the end of the 70s in our living rooms with the Atari and the Intellivision and stuff like that appearing. But they were still pretty crude, and what's more, you got what Atari or Intellivision decided you could have. There was no possibility of making your own games. And then, in 1980, this happened.
When it comes to video games, nobody compares to Atari.
I find Intellivision more sophisticated and lifelike.
Gentlemen, move over for my friend Vic. The Commodore VIC-20.
Move over.
The Commodore VIC-20 does more than your machines. It's a great computer that also plays great games. Like this, and this, and this.
A computer that plays great games?
Under $300?
Exactly.
We didn't know.
Get the Commodore VIC-20 computer for under
$300, or in fact under £200 in the UK. And I managed to persuade my dad that, yep, that was absolutely what was needed for my schooling. So I was lucky to get a VIC-20, and about the same time, my school got a Commodore PET. As you can see, I like Commodore. And these things opened my eyes to an amazing new thing, the notion of programming. Suddenly, I could make stuff appear on my TV screen, or that green screen, just by incantations, words. What eldritch wizardry is this? If this isn't magic, then what is? And I knew from that point, this is what I wanted to do with my life. Does anybody recognize that listing? You're all too shy or too young. Or it is certainly basic, and it was a game called The Valley that appeared in Computer and Video Game. No, it wasn't. It was Popular Computing Weekly. One of those things that you had to hand type in, and we carefully hand typed it in at school, and it took a very long time. So this was my new life. But how did we get to this point where suddenly kids in schools could play and program computers? So to do that, I'd like to just take you back in time a little bit, just to reflect on how we did get there. Hopefully everybody knows who this is. Haidee Lovelace. Haidee Lovelace. I prefer this picture to the other one that most people see. Charles Babbage referred to her as the enchantress of numbers, and yes, it's debatable as to whether or not she was the first programmer. I think she should get that credit. She was certainly the first published programmer when she wrote the first algorithm to calculate Bernoulli numbers. And you can see it is an algorithm as we would recognize it, an ordered list of statements of operators taking in input variables and output variables and registers. And had they built the analytical engine, it would have been programmed on these Jacquard loom cards, and Ada said, the analytical engine weaves algebraic patterns just as the Jacquard loom weaves flowers and leaves. And you get a sense then of where her head was. Even if you don't credit her with being the first programmer, what's special is that she was the first person to recognize that this had more potential than just being a better calculator. Babbage was just seeing this as the next generation of his difference engine. But Ada saw that this is a thing that could unleash human creativity. And she talked about how the individual and society might interact with this thing in the future to collaborate and to create music and things like that. Very, very ahead of her time. Unfortunately, we have to wait another century before we see the likes again. And we see these three gentlemen. Hopefully they're all recognizable. Obviously Alan Turing. In the middle, we have Claude Shannon and John von Neumann. And what they did for us was to think about the abstraction of what this thing might be that we call a computer as an abstraction from the mechanics of how we actually built them, away from the gears or the valves or the tubes. Turing coming up with the theory of computability, effectively, and what we would come to know as the Turing machine, the universal Turing machine. Shannon doing similar things with digital circuit theory at the same time, but then also doing the same thing for information processing and separating how we represent information and communicate it from the underlying mechanisms. And John von Neumann, who was a genius in many dimensions, coming up with the abstractions of how we might think about the components of a computer rather than it just being this hardwired machinery. So they laid down the abstractions that enabled us to start building things. And it wasn't until 1946, which is over 100 years after Ada and Charles Babbage were working on their analytical engine, that we see the first electronic Turing-complete machine. Incidentally, the analytical engine was Turing-complete, or would have been Turing-complete as well, and Ada's algorithm was bug-free. Not bad, really, considering it was never implemented. But as you can see on the left there, there's one of the first programmers, again a woman, programming ENIAC, and this represents the program for some calculating ballistics. A nightmare. It's all wiring, patch wiring, the individual components to program the device. So it wasn't really a programmable computer in the sense that we'd recognize it. And it's kind of interesting to reflect on how it's similar to Monaco GP with its hardwired circuitry. You wired in those logic gates and that's what you'd got. So programming it was a nightmare. Reprogramming it, you really didn't want to go there. So let's quickly go through the next few decades. So by the end of the 40s, we have computers, but computers are things that humans literally, physically manipulate to make a program with. We know there are probably around about the order of 50 programmers, and we know there are less than 5 computers by the end of the 40s. We know this because Thomas Watson, the founder of IBM, famously, allegedly said that he foresaw a market for as many as 5 computers in the future. It's arguable whether he actually said that, but it's been retrospectively considered that had he even said it in 1943, it would have held true for the next 10 years. So we know computers are horribly difficult to program. The people who are programming them are very deep-minded scientists and mathematicians. So throughout the 50s, some very clever people started to get fed up with the way programming was, and so assembly language starts to be introduced as a symbolic way of representing the programs. And so an abstraction layer is starting to appear between the physical machine and the programmer. So assembly appears, autocode. I'm giving Tony Brooker a shout out because he doesn't get enough credit for being really one of the first people to invent high-level languages. He worked on the Mark I at Manchester. He invented the notion of content-associative memory, and he was still the dean of my computer science department when I was an undergrad. At the same time, John Backus was doing Fortran, John McCarthy a little while later doing Lisp, and then Grace Hopper doing COBOL. Interesting that all of those folk cite the reason they did those things was because they were lazy, and they wanted to make it easier to program the computer. We also see the invention of transistors and microprogramming so that you can actually use the computer to load the programs in and do stuff for itself. And by now, we've gone up orders of magnitude with programmers and computers. Still, though, a lot more programmers than there are computers. So into the 60s, another abstraction layer starts to appear. Before now, we only have programs and computers, and your program is very much specific to that specific computer that you're programming. Early programs had to take into account all sorts of things like the speed in drum memory, the speed it was turning. You'd have to account for those kind of revolutions and timings just to be able to read the memory. Horrendous. So IBM was building quite a lot of computers by now and realized that it needed to have some kind of portability of programs so you could have a program run on more than one machine. So putting in operating systems was the beginnings of this layer of abstraction with OS 360. And then we get people like Kurtz and Company inventing BASIC, the beginner's all-purpose symbolic instruction code, realizing that more and more people were needed to program. So it had to be more and more people other than just really big-brain scientists and mathematicians. So basically it was an attempt to try and open it to the masses more. Christian Nygaard and Ole Dahl introduced Simula 67 as an alternative way of thinking about it, and that's introducing object orientation. And the guy with the hipster beard there, Edsger Dijkstra, tries to make programming more structured so that people could actually maintain programs going forward. So we notice now that people are starting to think about programs having a life cycle and living beyond just that task that they're there for. And most interestingly for us, I think, Ted Hoff at Intel invents the microprocessor, the Intel 4004. Largely thought to be a distraction, and it certainly wouldn't catch on. And by now, again, another order or two of magnitude for increase in programmers and computers. Still, we programmers outnumber the computers. So by the end of the 60s and into 70, I am born. I'm one, and we have a few more languages starting to appear. Nicholas Wirth having another crack at a beginner's language with Pascal. Alan Kay starting to develop Smalltalk. And Thompson and Ritchie, who in that photo unfortunately look like a weird Siamese twin pair, but they are actually two separate photos together, are developing Unix and C. And IBM introduces the concept of virtual machines on the mainframe as an attempt to get people to use the mainframe for more than just batch processing and to be able to get people to actually use it in an interactive way. Didn't catch on for a bit. And by now we're up to 1 million programmers. So in the 25 years, is it, we've gone from a very small handful of programmers to over 1 million and hundreds of thousands of computers. So throughout the 70s, we've got more languages. We start to see the fourth generation languages appearing as well. And Unix, of course, gaining ground, but also CP/M emerges as the microcomputer operating system. And DEC with their VMS, and another abstraction layer appears, because now suddenly computers are going to have to start to talk to each other, it seems. So IBM invented SNA. Has anybody had the pleasure of programming in SNA? Nobody's going to admit to it. Is anybody familiar with the OSI 7-layer architecture for networking? One person. Yeah. So that was like the most Byzantine way of thinking about networking, and the cheap and cheerful poor man's approach was TCP/IP, and these two went head to head. Okay. For me, the other important thing that happened at the beginning of the 70s was those things that Ted Hoff invented started to become interesting. And MOS Technologies, owned by Commodore, comes out with the 6502. Zilog comes out with the Z80, a refined version of the 8080. And Motorola bring out the 6809. And these three chips suddenly cause what I'm going to call the first Cambrian explosion, with the emergence of, first of all, the PET and the Apple, based on the 6502. Oh, at this point, Ken Olsen, the CEO of DEC, said, there is no reason why anybody would want a computer in their home. They missed the boat with that then. So the first Cambrian explosion arrives, and now we see dozens of different varieties of microcomputers appearing in people's houses, like me. And we're into the 80s. More languages, basically refinements of the same sort of things that have all gone before. Notice that by 1970, we'd done all of the inventing in terms of thinking about how programming languages might be, like functional languages with Lisp, with OO, with Simula 67. So we see more refinements of the concepts. And another abstraction starts to become important, because now we're needing graphics interfaces that are going to be portable, so X Windows starts to gain ground. And the next generation of microprocessors starts to occur. IBM, working with others, introduces this notion of RISC processors, but the CISC processors are doing very well at this time, and of course go into the IBM PC, and DOS appearing as a kind of hacked version of CP/M, and the original Mac based on the 68000. A few more interesting chips, Acorn looking for something to replace the 6502 and the B with, and the Amiga, which rocked everybody's world. How many people here were there when that Boeing demo came out for the first time? Man, we might as well just be the only two. It was like the world had completely changed. Nobody'd seen anything like that before. Unfortunately, the Amiga didn't succeed. What's also interesting, I think, is at this point, VLSI, very large-scale integration, becomes mainstream, and it's no longer possible for people to build chips by hand-drawing them on sheets of paper and cutting out the maps. From now on, we're going to have to use computers to design chips, which is kind of sad. So we're into the 90s. The open source movement is starting to emerge, and of course that brings with us Linux as a contender for the dominant OS. And further refinements. Now we're picking up the RISC architecture that got done in the previous decade. And we're also looking for ways to make use of all these transistors that we're getting year on year. So FPGAs start to be a thing that might work in the future. And then TBL comes along and he invents the web. And what he did effectively was introduce yet another abstraction on top of the networking, but to try and make information programmable effectively. Corba's doing its damnedest to try and define how computers should talk to each other. And we start to see, again, refinements of languages, but coupling this in with this notion of the web to try and make this information programming more of a language construct. And at this point, Robert Metcalfe, the inventor of Ethernet, the founder of 3Com, this is in the middle of the 90s when you've got talk about the information superhighway and all that kind of stuff. And he says, almost all of the many predictions now being made about 1996 hinge on the Internet's continuing exponential growth. But I predict the Internet will soon go spectacularly supernova and in 1996 catastrophically collapse. Well, it didn't, and we got more and more languages, scripting languages to try and help with building on top of the web. And so by the time we get to Y2K, we've got pretty much the OSs that we're going to see for the rest of our careers. We're seeing other ways to use transistors, to use them as graphics co-processors, sort of borrowing back from those days of the VIC. And web services as a way of trying to define how computers should talk together. So I just want to quickly go back to 1970, because I picked this book up. I found this in a print room at Hursley, which probably hadn't been read for about 30 years. And it's a fascinating book. I would really recommend you having a scan through this. It was written by Gerald Weinberg in 69, 70, but published in 71. So he's talking about, that era. And he was observing the difference between the amateur and the professional programmer. And of course, originally there was no such thing as a professional programmer. There was just programmers. Everybody was amateurs, effectively. But as time went on, we are seeing these strata layers appear, he said, which makes the amateur less aware of what's really going on inside the computer. And this is an interesting observation, because Alan Kay later on said, if you're serious about computers, you should really build your own. And I would wholly recommend that, and maybe get a chance to talk about that later as well. But he also, interestingly, as an aside, warned against some trends that he thought might disrupt the way programming happens in the future. This is 1970, remember, and he was saying that teams, you really don't want to have teams in silos. You want them to be all working together. In fact, you don't want individual programs. You should have them pairing together. You don't want to be setting artificial deadlines, and you've got to be careful about how you express goals. You certainly don't want to be measuring their progress and getting them to estimate how long it's going to take, because that's just going to make them lie. And also, you don't want programmers owning a program. You want them to be a team of multidisciplined, because it takes lots of different kinds of people. So you need a team of multidisciplined programmers to own the whole thing. Sound kind of familiar? And then at this point, waterfall comes in as the way that we do software, and it takes another 15 years to get rid of it. 15, 25 actually, yeah. Another interesting little observation that I liked from it was also he made a stab at what he thought the right traits for a programmer were, which I think probably hold true today. But I like the final thing of a good programmer avoids problems just as much as they solve problems. But the saving grace is that good programs are not made, sorry, they are made, they're not born, which gives stupid kids at school like me a chance to be able to become a good one. So we're into the 21st century now. Moore's Law, so far we've been eating what came to be known as the free lunch, where we were just piling transistors in each year and turning the clock up each year and getting performance hits, and it was great. And that all comes to an end. So, yes, we're still getting more transistors, but we can't crank up the clock enough because the thing would become as hot as the sun, literally, and then we can't cool it, so therefore we're going to have to keep the clock down, which is why we see clocks sort of maxing out around the 5 gigahertz. So we've got to do more with those transistors, so we start to build more cores into the same space. I picked this one. This is the cell processor that we did for Sony for the PlayStation 3. Because it was effectively, at the time we did it, a replication of a supercomputer on a chip. The same architecture as we used for Blue Gene, our gene-folding supercomputer. And its ability to get more and more processing by parallelizing work was a start of a shift. Parallelization, of course, becomes a trend, and so we're also building supercomputers by replicating things, and this was IBM's Roadrunner, IBM Roadrunner in Los Alamos, containing lots of cell processors inside. It was the first supercomputer to run over 1 million cores for the same problem. But it wasn't just supercomputers and building supercomputers in that way, but we saw people like Google capitalizing on using commodity hardware, but just scaling it out. So making things cheap, replicatable, and replicating the hell out of them. So this was going to be a trend that then, of course, gave rise to virtualization. So virtualization, everybody, I hope, should be very familiar now with how a hypervisor works, exposing the hardware up to a virtual layer that then multiple OSs can run on top of. And a kind of variation then came along with containerization, which is effectively virtualizing the kernel, and variations of those, all as ways of squeezing more power out of the same die, getting more portability, and basically lowering overheads of running applications over lots of machines. So this led us to then having what started to be called the data center as the computer. And it's interesting to reflect that as we went into deploying applications onto cloud applications and the challenges that then gave rise to DevOps, it was very similar to the challenges and the tensions that existed back in the mainframe days between programmers and the operators running the programs. So the programmer would get their program in a box of punch cards. They would have to take it to the operators to load, to run, and to provide the output. So there was this division, this siloing. And of course, that was a painful experience that nobody particularly enjoyed. And so we solved that by making the computers more programmable or meta-programmable so that programmers could self-serve themselves in running their programs. And of course, this is exactly what we did with DevOps. And we kind of did it by exposing those discrete compute and storage and networking components that you used to be able to see in physical boxes in the mainframe as virtual boxes, programming boxes in the APIs, building our software architecture out on top of that, and then building higher order services that would aggregate these things together. So the whole thing then starts to become an ecosystem that programmers then use to define infrastructure as code. So now we're not treating just our programs as code, but also the programmability of the computers, the infrastructure underneath it as well. Everything starts to become programmable. Everything starts to become code. And my goodness, didn't we take it far? I imagine probably everybody is using at least one item from each one of those major boxes. This is a nice kind of thing tracked out on GitHub to try and record all of the different frameworks. But it really does show you the layer upon layer upon layer of APIs and everything being treated as a programmable object. So whilst we're adding layers and layers and layers of APIs and programmability, remember we got all these transistors getting smaller and smaller, programmable elements becoming smaller and smaller, commoditized, flowing out everywhere. And so we now start to see the emergence of the Internet of Things. So we see these things appearing in virtually every device we have. We see them in, in our networks, in our cars, in our headphones, in our homes and buses. And also then using those cloud computing data centers to be able to control and augment what's going on by leveraging this embedded computability, this embedded programmability out throughout the world. But of course the programming model has to shift a little bit now because we can't use procedural kind of approaches so much like that. So we have to shift now towards more of an event-driven architecture, which is interesting because, of course, event-driven architectures are what embedded programmers have been used to for decades as well. So all of this stuff is why we're coming into now the era that we in IBM refer to as the cognitive era, and our approach to that with IBM Watson is because the explosion of sensors and compute and information is just beyond ridiculous. I mean, these numbers, even if they were 2 orders or 3 orders of magnitude out, would still be completely enormous. And what's also interesting is that we have gone way past that point where there were more programmers than computers. Now there are not only more computers than programmers, there are more computers than human beings. And this trend will just escalate and escalate, which results then in something like 75% of the stuff flowing around that we're having to deal with being unstructured. And unstructured data really needs a different way of approaching it from our traditional ways of programming, and this is where machine learning is becoming so popular. Having the computer be able to augment how we think of and deal with writing programs and processing this vast volume is clearly the way we're going to be going for the next 10 years. But just on that path, as we're seeing, going through bare metal VMs, containers, we're now seeing functions as a service or serverless architectures becoming the next trend, because in an ever-increasing attempt to try and bring down the cost of computing and to make the execution of a function as lightweight as possible. This function as a service model, and we're using the Apache OpenWhisk project in Bluemix. Other options are available. As a way of then making the discrete elements of what it takes to build a complex application in this kind of modern world as lightweight as possible. Couple that with lots of embedded logic out at the edges, and then using higher order logic to be able to compose these things together. But for me, what really is interesting is the way this explosion, this democratization of compute elements has really started a new movement. And this is what I'm sort of going to refer to as the second Cambrian explosion. Thinking back to in the end of the 70s, the beginning of the 80s, that explosion of availability of computers into a realm that never would have dreamt, even just a couple of years ago, that they would get their hands on a computer. Same thing's happening now with a whole another demographic of people that would never have considered themselves to be interested in computers. But this democratization of digital fabrication is really changing everything. The availability of additive or subtractive manufacturing techniques. How many people have got a 3D printer in the room? Only 2? Okay. How many people have got a laser cutter or a CNC machine? A few more. I bet lots of people have got microcontrollers like Arduinos or anything like that. Yeah, a little bit more. And DIY electronics, enabling people to literally build anything from scratch in their own home. No longer do they have to wait for some corporation to manufacture something for them to use. Now you can really make it in your own home. Like this is just a little project that somebody's going to go kickstarting with to do printable PCBs at home. The thing is, this is also giving rise to an increase in amateur roboticists as well. So not very long ago, somebody trying to build a robot at home would have been a hopeless, ridiculous task. But now everybody's doing it. And this is a shout out to the guys down on the floor there in the IBM booth doing the mad scientist thing. That group of people are IBMers who are just doing this for the fun of things, just interesting. And this is my friend Luc Derosier's personal project. Trevor, the robot, he's French-Canadian, so naming in English probably isn't his strength thing. But sorry to anybody called Trevor. So he's just got commodity pieces together, built the circuits, built the logic, and he's using Bluemix Cloud services and other services to be able to then do computer vision analysis, to be able to interpret what the thing is seeing and to be able to guide it as well. So effectively an autonomous robot being controlled by logic that is hosted in the cloud wirelessly. And this is being replicated in all manner of different fields and areas. One of my favorite websites, hackaday.io, is just an incredible melting pot of creativity. There's people doing all kinds of stuff with all kinds of different technologies, not just any one in particular, but it's those mashups of things. And it's these mashing up because, again, everything is programmable. I've noticed on the front of the Magpie magazine this week, I got a Google build your own AI voice reco thing. The recognition of the importance of the hobbyist, the amateur. And again, going back to the early hobbyists in the mid-70s, the only people using those 6502 or Z80 chips were hobbyists, like Wozniak and Jobs. Okay, they were building their own computers from scratch, and this gave rise to an entire industry. I think we're seeing this in multiple dimensions now, in many different kinds of industries. And this one I particularly like, because this is something I'm playing about with at the moment, is making use of those things that were just coming out in the 90s, the FPGAs. People are finding all kinds of really interesting way to use them because they are so cheap now. A board like that you can buy on eBay for £10, and it is incredible. I'm using mine to replicate early 8-bit microcomputers, systems as a chip, all just programming it using VHDL. So you see down at the bottom there, VHDL descended from Ada. Ada was a language that was introduced by the military in the 70s because there were too many languages by then and they needed to standardize. So they chose Ada as a way of saying if you're going to work on a defense project, you do it in Ada. So very good at event-driven processing. You've got a whole fab plant, effectively, on your desktop when you're using FPGAs. You can do whatever you like. Now, remember, we were sort of going away from specialized stuff to more generalized stuff throughout the ages. But now it's easy to do that specialized stuff because it's programmable. On the left-hand side, we've got some OpenCL as a way of building applications then that you can just throw at multiple cores and it be executed on those cores. So you can write little OpenCL programs, which are basically in C, compile them and run them on your GPU without having the horrible funk of having to control and load up individually programs into those GPUs or FPGAs or whatever accelerator you have plugged into your machine. And now, just in the last few months, really, we're seeing FPGAs become the new thing in cloud computing. So many of the popular public clouds now have nodes that include FPGAs, and really beefy FPGAs, I might add, available. So you can not only control your infrastructure as code at the macro level, your infrastructure as code can also include that really silicon level. So you can, for a particular workload, whether it's blockchain or whatever, you can build specialized accelerator logic and deploy that along with everything else as part of your cloud deployment. So this kind of brings me up to where are we going now? How many people saw the keynote this morning from the guy from Sussex? Yeah, I was really pleased to see what Sussex was doing with quantum computing. So, computer scientists, we like to break up the world into the set of problems, the set of easy problems being P, solvable in polynomial time, the set of hard problems or non-polynomial time solvable on the outside, and those really hard ones as being NP complete around the edge. And of course those hard ones and hardest ones we just can't do anything with because, as we heard this morning, with our computers as exist today, there's just no hope of solving those things in any sort of reasonable time frame. But it turns out that with a quantum computer, a good subset of those hard and hardest problems suddenly become easy. So they suddenly become accessible. Things that we thought we would never be able to solve suddenly become potentially solvable. And not just solvable, but a problem that would take thousands of years to solve on a classical computer, if at all, would take seconds to minutes on a quantum computer. And as also mentioned this morning, there's a set of problems that we couldn't even possibly address beyond NP hardest, like simulating quantum effects, suddenly becomes a possibility. And of course there are lots of well-known hard problems that fit into this space and become easy, like the factoring problem. You know, the notion of being able to crack the desencryption algorithm within seconds on a quantum computer. So quantum computers are really good at doing search. As we heard this morning, it has qubits instead of bits. It still has the notion of zeros and ones, effectively. What's kind of interesting is, you know, in our classical computers, zeros and ones are still just representations of a voltage. You know, if the voltage is low, it's a 0, and if the voltage is high, it's a 1. Effectively the same deal with quantum, where we've got sort of energy levels. If energy level's low, then it's a 0, and if it's high, it's a 1. And then you've got this weird thing called superposition, which is and everything in between, or both of them, or everything. But nevertheless, let's not worry about that so much. We've got bits, so we understand bits. And then we can string these bits together, like we do in classical computers. We form registers. And so you can form registers in a quantum computer, and using this weird stuff called entanglement, you can get some relationship together. And also, as was explained, and it's a really difficult thing to get your head around, well, I find it difficult, is that it's not just that with a binary register in a classic computer can represent one possible solution in a problem space at any one time. With the qubit register, you can have it represent all of the solutions in the problem space at any one time. So being able to search the entire space in one pass and get the measurement back, rather than having to iterate around, is it this, compare and contrast, is it this, compare and contrast, etc., in an iterative way. You can do it in this super parallel way. I did genetic algorithms when I did my degree, which have somewhat fallen out of favour as well. But it seems to me this would be a perfect technique for that, because you had to generate enormous gene pools of solutions and then evaluate whether this particular gene was fit or not. You could do this all in one pass. And then when you measure the result, it sort of collapses back to a particular solution. And we recognize that the way that we're going to use this is effectively a quantum computer will be an accelerator for a classical computer. We'll model the setup in a classical computer, set it off in a quantum computer, and the measurement returns the result. But what's interesting is it's still just the same. We have these logic gates, effectively. We've got a controlled NOT gate, which is this 2-bit operator, which is kind of the equivalent of a NAND gate, effectively. You know, you can build any circuit with a NAND gate. Similarly with the CNOT. And you've got this weird thing called a Hadamard gate, which sets everything up into this superposition, this kind of make it every possible value. But what I like is that we talk about, in quantum computing, you're assembling circuits. So we're right back to the beginning of you're just wiring up a circuit. How many people have seen our quantum computer on the cloud? So what was interesting, the Sussex guys are doing ion trap. We're doing superconductor model. In the same way, in sort of the 40s, 50s, it wasn't clear which way to go with memory. Would it be ferrite core? Would it be sort of Selectron tube, vacuum tubes? And it wasn't evident which one was going to win for a while. We're kind of in the same place. There's different ways of modeling qubits. Why we like superconducting is that we can fabricate the chips using our existing fabrication technologies. So you've got a little magnification of a 5-qubit circuit there that we print onto wafer. We run it at 5 gigahertz, so it's looking very much like our existing computers. The only trouble is we've got to get it down to 10 millikelvin to keep it stable and keep the coherence. So you ain't going to see that on your desktop anytime soon.
You know offhand between ion or superconductive or a third option, what Google's doing with their 40-bit?
I'm not sure. My guess, without having any facts to hand, is it's like quantum annealing, the same that D-Wave does, but which is kind of just a kind of a not as effective, but you get a little bit of a boost.
The one they're doing in Santa Barbara.
I don't know. What I do know is that we've got to get... We're at 5 to 7 bits at the moment. We need to get to about 50 qubits before things become really worth doing. But we're seeing this 10 times improvement on our speeds every 2 years. So we think within 10 years we could see that sort of order. And this is what we've made available on our Bluemix cloud so that you can write your own programs in quantum assembly language, Chasm, Open Chasm. You basically build these circuits. There's a visual representation for constructing the circuits and doing the entanglement and the Hadamard gates and stuff. Or you can write it out in the symbolic assembler over there. You can write that, you can run it on a simulator. At the moment, the simulator is quicker than the real thing. But as we get more qubits, that won't be the case. But you can run it on the real one, and you can basically submit it like a batch processing. It's like handing your punch cards over. An operator runs it and gives you the results back. Already there's been something like 110 research papers published worldwide off the back of running experiments in our IBM Q. So, going back to where I came in at the beginning of this talk, why do I love being a programmer? Well, I think we've come a very, very long way. Everything, almost everything we can think of, from the subatomic to the global scale, is programmable. We've reduced everything to being an API and a programmable model. And for me, it's still a magical experience. This is nothing about technology. This is about creativity. Why now? Well, at the beginning, as we saw, there was no distinction between user of a computer and programmer of a computer. There was just the one person. We saw this divergence, but with these Cambrian explosions, we see more and more people getting dragged into and touching and being exposed to the notion of programming the computer. We also saw this distinction between amateur and professional. Going back to Weinberg's definition of what made a professional, not understanding an amateur, not understanding what's fully going on in the computer from the electrical level up. How many people would consider themselves to be a professional by that definition today? And of course, more and more people who never consider themselves to be programmers are programming. Also, that distinction between hardware and software. We added those layers of abstraction, yes. But we're also back to programming at not just the silicon level, but at the subatomic level. And that notion of specialized and generalized, those initial computers being built pretty much for one task, going more and more generalized, but now realizing that specialization is good for particular problem spaces. And so being able to incorporate that specialization within the context of a generalized programming model. So I feel like we're stood somewhere around about 1939, 1940. You know, we've got a vision of where we want to go. We haven't got a clue what's set in stone. You know, by 1970, we'd nailed all of the real problems, right? And everything else was just refinements and recursion and, you know, sort of making it a little bit easier. But all of the problems, all of the, you know, choices had kind of been nailed. We're not there with quantum. Everything's still open, and including the programming models. We heard that call this morning to arms of people doing more programming, getting involved with quantum computing. You could be another Claude Shannon. You never know. But with all that blank sheets of paper, I would like to just remember, I've just run out of time, I've got 2 slides left. Creativity is stimulated by constraints. On the one hand, over there, I've got this, I just pulled this as a wonderful example of a retro hack where somebody's ported Slack, a Slack client, to a real Commodore 64, not just the emulator, so he actually interfaces to Slack via 64. And how many people have heard about fantasy consoles? A few. People, basically, these consoles recreate what it would be like to create a game in an 8-bit environment, artificially constraining you know, the number of colours, the size of the memory, etc. And the creativity is incredible, far, far better than it was in the 80s. And creativity is really important. That's why I got into being a programmer. This is a quote from Tolkien's poem Mythopia. Tolkien considered that it was our God-given gift to be able to create, or sub-create as he referred to it. It's a part of what makes us human. And Grady Booch, at a talk at the History of Computing Museum, said, software is the hidden writing of the whispers the stories of possibility to our hardware. We are the storytellers. Just one last quote. I'll read it in case you can't see it. I've quoted a lot of quotes that we really went bad. When wireless is perfectly applied to the whole Earth, is perfectly applied, the whole Earth will be converted to a huge brain. We shall be able to communicate with one another instantly, irrespective of distance. Not only this, but through television and telephony, we shall see and hear one another as perfectly as though we were face to face, despite intervening distances of thousands of miles. And the instruments through which we shall be able to do this will be amazingly simple compared with our present telephone. A man will be able to carry one in his vest pocket. Anybody know who said that? Tesla. And do you know when? 1926, 10 years before Turing. Thank you very much. I think I'm way over time, so I don't know whether or not there's an opportunity. So, but grab me afterwards and talk. Thank you.